Wave optics. Introduction. In 1637 Descartes gave the corpuscular model of light and derived Snell's law. It explained the laws of reflection and refraction of light at an interface. The corpuscular model predicted that if the ray of light, on refraction, bends towards the normal, then the speed of light would be greater in the second medium. This corpuscular model of light was further developed by Isaac Newton in his famous book entitled Optics, and because of the tremendous popularity of this book, the corpuscular model is very often attributed to Newton. In 1678, the Dutch physicist Christiaan Huygens put forward the wave theory of light. It is this wave model of light that we will discuss in this chapter. As we will see, the wave model could satisfactorily explain the phenomena of reflection and refraction. However, it predicted that on refraction, if the wave bends towards the normal, then the speed of light would be less in the second medium. This is in contradiction to the prediction made by using the corpuscular model of light. It was much later confirmed by experiments where it was shown that the speed of light in water is less than the speed in air, confirming the prediction of the wave model. Foucault carried out this experiment in 1850. The wave theory was not readily accepted primarily because of Newton's authority and also because light could travel through vacuum. It was felt that a wave would always require a medium to propagate from one point to the other. However, when Thomas Young performed his famous interference experiment in 1801, it was firmly established that light is indeed a wave phenomenon. The wavelength of visible light was measured and found to be extremely small. For example, the wavelength of yellow light is about 0.6 micrometer. Because of the smallness of the wavelength of visible light, in comparison to the dimensions of typical mirrors and lenses, light can be assumed to approximately travel in straight lines. This is the field of geometrical optics, which we had discussed in the previous chapter. Indeed, the branch of optics in which one completely neglects the finiteness of the wavelength is called geometrical optics, and the ray is defined as the path of energy propagation in the limit of wavelength tending to zero. After the interference experiment of Young in 1801, for the next 40 years or so, many experiments were carried out involving the interference and diffraction of light waves. These experiments could only be satisfactorily explained by assuming a wave model of light. Thus, around the middle of the 19th century, the wave theory seemed to be very well established. The only major difficulty was that since it was thought that a wave required a medium for its propagation, how could light waves propagate through vacuum? This was explained when Maxwell put forward his famous electromagnetic theory of light. Maxwell had developed a set of equations describing the laws of electricity and magnetism, and using these equations he derived what is known as the wave equation, from which he predicted the existence of electromagnetic waves. From the wave equation, Maxwell could calculate the speed of electromagnetic waves in free space, and he found that the theoretical value was very close to the measured value of speed of light. From this, he propounded that light must be an electromagnetic wave. Thus, according to Maxwell, light waves are associated with changing electric and magnetic fields. Changing electric field produces a time and space varying magnetic field, and a changing magnetic field produces a time and space varying electric field. The changing electric and magnetic fields result in the propagation of electromagnetic waves, or light waves, even in vacuum. In this chapter we will first discuss the original formulation of the Huygens principle and derive the laws of reflection and refraction. In sections 10.4 and 10.5, we will discuss the phenomenon of interference, which is based on the principle of superposition. In section 10.6 we will discuss the phenomenon of diffraction, which is based on Huygens' Fresnel principle. Finally, in section 10.7 we will discuss the phenomenon of polarization, which is based on the fact that the light waves are transverse electromagnetic waves. Huygens' principle. We would first define a wavefront. When we drop a small stone on a calm pool of water, waves spread out from the point of impact. Every point on the surface starts oscillating with time. At any instant, a photograph of the surface would show circular rings on which the disturbance is maximum. Clearly, all points on such a circle are oscillating in phase because they are at the same distance from the source. Such a locus of points, which oscillate in phase, is called a wavefront. Thus a wavefront is defined as a surface of constant phase. The speed with which the wavefront moves outwards from the source is called the speed of the wave. The energy of the wave travels in a direction perpendicular to the wavefront. If we have a point source emitting waves uniformly in all directions, then the locus of points which have the same amplitude and vibrate in the same phase are spheres, and we have what is known as a spherical wave, as shown in figure 10.1. At a large distance from the source, a small portion of the sphere can be considered as a plane, and we have what is known as a plane wave, figure 10.1b. Now, if we know the shape of the wavefront at t equals 0, then Huygens' principle allows us to determine the shape of the wavefront at a later time tau. Thus, Huygens' principle is essentially a geometrical construction, which given the shape of the wavefront at any time allows us to determine the shape of the wavefront at a later time. Let us consider a diverging wave and let f1, f2 represent a portion of the spherical wavefront at t equals 0. Now, according to Huygens' principle, each point of the wavefront is the source of a secondary disturbance, and the wavelets emanating from these points spread out in all directions with the speed of the wave. These wavelets emanating from the wavefront are usually referred to as secondary wavelets, and if we draw a common tangent to all these spheres, we obtain the new position of the wavefront at a later time. Huygens' principle. Each point of the wavefront is the source of a secondary disturbance, and the wavelets emanating from these points spread out in all directions with the speed of the wave. These wavelets emanating from the wavefront are usually referred to as secondary wavelets, and if we draw a common tangent to all these spheres, we obtain the new position of the wavefront at a later time. Thus, if we wish to determine the shape of the wavefront at t equals tau, we draw spheres of radius v tau from each point on the spherical wavefront, where v represents the speed of the waves in the medium. If we now draw a common tangent to all these spheres, we obtain the new position of the wavefront at t equals tau. The new wavefront shown as G1 G2 in figure 10.2 is again spherical with point O as the center. The above model has one shortcoming. We also have a backwave which is shown as D1 D2 in fig. 10.2. Huygens argued that the amplitude of the secondary wavelets is maximum in the forward direction and 0 in the backward direction. By making this ad hoc assumption, Huygens could explain the absence of the backwave. Huygens, this ad hoc assumption is not satisfactory, and the absence of the backwave is really justified from more rigorous wave theory. In a similar manner, we can use Huygens' principle to determine the shape of the wavefront for a plane wave propagating through a medium, figure 10.3. Refraction and reflection of plane waves using Huygens' principle. Refraction of a plane wave. We will now use Huygens' principle to derive the laws of refraction. Let pp' represent the surface separating medium 1 and medium 2, as shown in figure 10.4. Let v1 and v2 represent the speed of light in medium 1 and medium 2 respectively. We assume a plane wavefront AB propagating in the direction A' are incident on the interface at an angle I as shown in the figure. Let tau be the time taken by the wavefront to travel the distance bc. Thus, bc equals v1 tau. In order to determine the shape of the refracted wavefront, we draw a sphere of radius v2 tau from the point A in the second medium. The speed of the wave in the second medium is v2. Let CE represent a tangent plane drawn from the point C onto the sphere. Then, air equals v2 tau, and CE would represent the refracted wavefront. If we now consider the triangles ABC and AEC, we readily obtain the following equations 10.1 and 10.2, where I and R are the angles of incidence and refraction, respectively. Thus we obtain the equation 10.3. From the above equation, we get the important result that if R less than I, that is if the ray bends toward the normal, the speed of the light wave in the second medium, v2, will be less than the speed of the light wave in the first medium, v1. This prediction is opposite to the prediction from the corpuscular model of light, and as later experiments showed, the prediction of the wave theory is correct. Now, if c represents the speed of light in vacuum, then, we get the equations 10.4 and 10.5, which are known as the refractive indices of medium 1 and medium 2, respectively. In terms of the refractive indices, equation 10.3 can be written as n1 sin I equals n2 sin R. This is the Snell's law of refraction. Further, if λ1 and λ2 denote the wavelengths of light in medium 1 and medium 2, respectively, and if the distance bc is equal to λ1, then the distance r will be equal to λ2, because if the crest from B has reached C in time tau, then the crest from A should have also reached E in time tau. Thus, we get the equation 10.7. The above equation implies that when a wave gets refracted into a denser medium, v1 greater than v2, the wavelength and the speed of propagation decrease, but the frequency nu equals v lambda remains the same. Refraction at a rarer medium. We now consider refraction of a plane wave at a rarer medium, that is V2 greater than V1. Proceeding in an exactly similar manner, we can construct a refracted wavefront as shown in figure 10.5. The angle of refraction will now be greater than angle of incidence. However, we will still have n1 sin I equals n2 sin r. We define an angle IC by the following equation 10.8. Thus, if I equals IC, then sin r equals 1 and r equals 90 degrees. Obviously, for I greater than IC, there cannot be any refracted wave. The angle IC is known as the critical angle, and for all angles of incidence greater than the critical angle, we will not have any refracted wave and the wave will undergo what is known as total internal reflection. The phenomenon of total internal reflection and its applications was discussed in section 9.4. Reflection of a plane wave by a plane surface. We next consider a plane wave AB incident at an angle I on a reflecting surface Mn. If v represents the speed of the wave in the medium and if tau represents the time taken by the wavefront to advance from the point B to C, then the distance BC equals v tau. In order to construct the reflected wavefront, we draw a sphere of radius v tau from the point A as shown in Fig. 10.6. Let CE represent the tangent plane drawn from the point C to this sphere. Obviously, air equals BC equals v tau. If we now consider the triangles EAC and BAC, we will find that they are congruent and therefore, the angles I and R, as shown in figure 10.6, would be equal. This is the law of reflection. Once we have the laws of reflection and refraction, the behavior of prisms, lenses, and mirrors can be understood. These phenomena were discussed in detail in Chapter 9 on the basis of rectilinear propagation of light. Here we just describe the behavior of the wavefronts as they undergo reflection or refraction. In figure 10.7, we consider a plane wave passing through a thin prism. Clearly, since the speed of light waves is less in glass, the lower portion of the incoming wavefront, which travels through the greatest thickness of glass, will get delayed, resulting in a tilt in the emerging wavefront as shown in the figure. In figure 10.7b, we consider a plane wave incident on a thin convex lens. The central part of the incident plane wave traverses the thickest portion of the lens and is delayed the most. The emerging wavefront has a depression at the center and therefore the wavefront becomes spherical and converges to the point F, which is known as the focus. In figure 10.7c, a plane wave is incident on a concave mirror, and on reflection we have a spherical wave converging to the focal point F. In a similar manner, we can understand refraction and reflection by concave lenses and convex mirrors. From the above discussion, it follows that the total time taken from a point on the object to the corresponding point on the image is the same measured along any ray. For example, when a convex lens focuses light to form a real image, although the ray going through the center traverses a shorter path, but because of the slower speed in glass, the time taken is the same as for rays traveling near the edge of the lens. Coherent and incoherent addition of waves. In this section we will discuss the interference pattern produced by the superposition of two waves. Indeed, the entire field of interference is based on the superposition principle, according to which at a particular point in the medium, the resultant displacement produced by a number of waves is the vector sum of the displacements produced by each of the waves. Consider two needles S1 and S2 moving periodically up and down in an identical fashion in a trough of water, figure 10.8. They produce two water waves, and at a particular point, the phase difference between the displacements produced by each of the waves does not change with time. When this happens, the two sources are said to be coherent. Figure 10.8b shows the position of crests, solid circles, and troughs, dashed circles, at a given instant of time. Consider a point P for which S1P equals S2P.
Since the distances S1P and S2P are equal, waves from S1 and S2 will take the same time to travel to the point P, and waves that emanate from S1 and S2 in phase will also arrive at the point P in phase. Thus, if the displacement produced by the source S1 at the point P is given by y1 equal to a cos omega t, then the displacement produced by the source S2 at the point P will also be given by y2 equal to a cos omega t. Thus, the resultant of displacement at P would be given by y equal to y1 plus y2, that's equal to 2a cos omega t. Since the intensity is proportional to the square of the amplitude, the resultant intensity will be given by I equal to 4 times I naught. where I0 represents the intensity produced by each one of the individual sources. I0 is proportional to A square. In fact, at any point on the perpendicular bisector of S1 S2, the intensity will be 4 times I0. The two sources are said to interfere constructively, and we have what is referred to as constructive interference. We next consider a point Q given in the figure 10.9a, for which S2Q minus S1Q equal to 2 lambda. The waves emanating from S1 will arrive exactly 2 cycles earlier than the waves from S2 and will again be in phase, which is given in figure 10.9a. Thus, if the displacement produced by S1 is given by y1 equal to a cos omega t, then the displacement produced by S2 will be given by y2 equal to a cos omega t minus 4 pi, and that's equal to a cos omega t, where we have used the fact that a path difference of 2 lambda corresponds to a phase difference of 4 pi. The two displacements are once again in phase, and the intensity will again be 4 times I0, giving rise to constructive interference. In the above analysis, we have assumed that the distances S1Q and S2Q are much greater than d, which represents the distance between S1 and S2, so that although S1Q and S2Q are not equal, the amplitudes of the displacement produced by each wave are very nearly the same. We next consider a point R, for which S2R minus S1R equal to minus 2.5 lambda. The waves emanating from S1 will arrive exactly 2.5 cycles later than the waves from S2. Thus, if the displacement produced by S1 is given by y1 equal to a cos omega t, then the displacement produced by S2 will be given by y2 equal to a cos omega t plus 5 pi, and thus equal to minus a cos omega t.
Where we have used the fact that a path difference of 2.5 lambda corresponds to a phase difference of 5 pi. The two displacements are now out of phase, and the two displacements will cancel out to give zero intensity. This is referred to as destructive interference. Now, to summarize, if we have two coherent sources S1 and S2 vibrating in phase, then for an arbitrary point P, whenever the path difference S1P difference S2P is equal to n lambda, where n is equal to 0, 1, 2, 3, etc., we will have constructive interference, and the resultant intensity will be 4 times I0. The sign difference between S1P and S2P represents the difference between S1P and S2P. On the other hand, if the point P is such that the path difference S1P difference S2P is equal to n plus half times lambda, where n is equal to 0, 1, 2, 3, etc., we will have destructive interference, and the resultant intensity will be 0. Now, for any other arbitrary point G, as shown in the figure 10.10, let the phase difference between the two displacements be phi. Thus, if the displacement produced by S1 is given by y1 equal to a cos omega t, then the displacement produced by S2 would be y2 equal to a cos omega t plus phi. And the resultant displacement will be given by y equal to the sum of the displacements y1 and y2, that is y1 plus y2. And that's equal to a times cos omega t plus phi, and that's equal to 2a cos phi by 2 cos omega t plus phi by 2. That comes from cos a plus cos b equal to 2 cos a plus b by 2 cos a minus b by 2. The amplitude of the resultant displacement is 2a cos phi by 2, and therefore the intensity at that point will be I equal to 4 times I0 cos square phi by 2. If phi equal to 0, plus or minus 2 pi, plus or minus 4 pi, etc., which corresponds to the condition given by equation 10.9, we will have constructive interference, leading to maximum intensity. On the other hand, if phi is equal to plus or minus pi, plus or minus 3 pi, plus or minus 5 pi, which corresponds to the condition given by equation 10.10, we will have destructive interference leading to zero intensity. Now, if the two sources are coherent, that is, if the two needles are going up and down regularly, when the phase difference phi at any point will not change with time, and we will have a stable interference pattern. That is, the positions of maxima and minima will not change with time. However, if the two needles do not maintain a constant phase difference, then the interference pattern will also change with time, and if the phase difference changes very rapidly with time, The positions of maxima and minima will also vary rapidly with time, and we will see a time averaged intensity distribution. When this happens, we will observe an average intensity that will be given by I is equal to 2 times I naught at all points.
When the phase difference between the two vibrating sources changes rapidly with time, we say that the two sources are incoherent, and when this happens the intensities just add up. This is indeed what happens when two separate light sources illuminate a wall. Interference of light waves and Young's experiment. We will now discuss interference using light waves. If we use two sodium lamps illuminating two pinholes, figure 10.11, we will not observe any interference fringes. This is because of the fact that the light wave emitted from an ordinary source, like a sodium lamp, undergoes abrupt phase changes in times of the order of 10⁻⁻10 seconds. Thus the light waves coming out from two independent sources of light will not have any fixed phase relationship and would be incoherent. When this happens, as discussed in the previous section, the intensities on the screen will add up. The British physicist Thomas Young used an ingenious technique to lock the phases of the waves emanating from S1 and S2. He made two pinholes S1 and S2, very close to each other, on an opaque screen, figure 10.12. These were illuminated by another pinholes that was in turn lit by a bright source. Light waves spread out from S and fall on both S1 and S2. S1 and S2 then behave like two coherent sources because light waves coming out from S1 and S2 are derived from the same original source, and any abrupt phase change in S will manifest in exactly similar phase changes in the light coming out from S1 and S2. Thus, the two sources S1 and S2 will be locked in phase. That is, they will be coherent like the two vibrating needle in our water wave example, figure 10.8. The spherical waves emanating from S1 and S2 will produce interference fringes on the screen GG-, as shown in figure 10.12b. The positions of maximum and minimum intensities can be calculated by using the analysis given in section 10.4.
We will have constructive interference resulting in a bright region when xd by d is equal to n lambda. That is, x is equal to xn, that's equal to n lambda d by d, where n is equal to 0, plus or minus 1, plus or minus 2, etc. On the other hand, we will have destructive interference resulting in a dark region when xd by d is equal to n plus half lambda, that is, x is equal to xn, that's equal to n plus half lambda d by d, where n is equal to 0, plus or minus 1, plus or minus 2. Thus, dark and bright bands appear on the screen as shown in the figure 10.13. Such bands are called fringes. Equations 10.13 and 10.14 show that dark and bright fringes are equally spaced. That's the difference between interference pattern and diffraction pattern. Now, let us see what is diffraction. If we look clearly at the shadow cast by an opaque object close to the region of geometrical shadow, there are alternate dark and bright regions just like in interference. This happens due to the phenomenon of diffraction. Diffraction is a general characteristic exhibited by all types of waves, be it sound waves, light waves, water waves, or matter waves. Since the wavelength of light is much smaller than the dimensions of most obstacles, we do not encounter diffraction effects of light in everyday observations.
However, the finite resolution of our eye or of optical instruments such as telescopes or microscopes is limited due to the phenomenon of diffraction. Indeed, the colors that you see when a CD is viewed is due to diffraction effects. We will now discuss the phenomenon of diffraction. The single slit. In the discussion of Young's experiment, we stated that a single narrow slit acts as a new source from which light spreads out. Even before Young, early experimenters, including Newton, had noticed that light spreads out from narrow holes and slits. It seems to turn around corners and enter regions where we would expect a shadow. These effects, known as diffraction, can only be properly understood using wave ideas. After all, you are hardly surprised to hear sound waves from someone talking around a corner. When the double slit in Young's experiment is replaced by a single narrow slit, illuminated by a monochromatic source, a broad pattern with a central bright region is seen. On both sides, there are alternate dark and bright regions, the intensity becoming weaker away from the center, figure 10.15. To understand this, go to figure 10.14, which shows a parallel beam of light falling normally on a single slit lane of width A. The diffracted light goes on to meet a screen. The midpoint of the slit is M. A straight line through M perpendicular to the slit plane meets the screen at C. We want the intensity at any point P on the screen. As before, straight lines joining P to the different points L, M, N, etc., can be treated as parallel, making an angle theta with the normal MC. The basic idea is to divide the slit into much smaller parts, and add their contributions at P with the proper phase differences. We are treating different parts of the wavefront at the slit as secondary sources. Because the incoming wavefront is parallel to the plane of the slit, these sources are in phase. It is observed that the intensity has a central maximum at theta equals 0 and other secondary maxima at theta L, n plus 1/2, lambda by A, which go on becoming weaker and weaker with increasing n. The minima, 0 intensity, are at theta ln lambda by A, n equals plus or minus 1, plus or minus 2, plus or minus 3. The photograph and intensity pattern corresponding to it is shown in figure 10.15. There has been prolonged discussion about difference between interference and diffraction among scientists since the discovery of these phenomena. In this context, it is interesting to note what Richard Feynman has said in his famous Feynman lectures on physics. No one has ever been able to define the difference between interference and diffraction satisfactorily. It is just a question of usage, and there is no specific, important physical difference between them. The best we can do is, roughly speaking, is to say that when there are only a few sources, say 2 interfering sources, then the result is usually called interference, but if there is a large number of them, it seems that the word diffraction is more often used. In the double slit experiment, we must note that the pattern on the screen is actually a superposition of single slit diffraction from each slit or hole, and the double slit interference pattern. Seeing the single slit diffraction pattern. It is surprisingly easy to see the single slit diffraction pattern for oneself. The equipment needed can be found in most homes, 2 razor blades and 1 clear glass electric bulb, preferably with a straight filament. One has to hold the 2 blades so that the edges are parallel and have a narrow slit in between. This is easily done with the thumb and forefingers, figure 10.16. Keep the slit parallel to the filament, right in front of the eye. Use spectacles if you normally do. With slight adjustment of the width of the slit and the parallelism of the edges, the pattern should be seen with its bright and dark bands. Since the position of all the bands, except the central one, depends on wavelength, they will show some colors. Using a filter for red or blue will make the fringes clearer. With both filters available, the wider fringes for red compared to blue can be seen. In this experiment, the filament plays the role of the first slit S in figure 10.15. The lens of the eye focuses the pattern on the screen, the retina of the eye. With some effort, one can cut a double slit in an aluminium foil with a blade. The bulb filament can be viewed as before to repeat Young's experiment. In daytime, there is another suitable bright source subtending a small angle at the eye. This is the reflection of the sun in any shiny convex surface, example a cycle bell. Do not try direct sunlight, it can damage the eye and will not give fringes anyway, as the sun subtends an angle of 1/2. In interference and diffraction, light energy is redistributed. If it reduces in one region, producing a dark fringe, it increases in another region, producing a bright fringe. There is no gain or loss of energy, which is consistent with the principle of conservation of energy. Polarization. Consider holding a long string that is held horizontally, the other end of which is assumed to be fixed. If we move the end of the string up and down in a periodic manner, we will generate a wave propagating in the plus x direction, figure 10.17. Such a wave could be described by the following equation 10.15, where R and omega represent the amplitude and the angular frequency of the wave, respectively. Further, the equation 10.16 represents the wavelength associated with the wave. Since the displacement, which is along the y direction, is at right angles to the direction of propagation of the wave, we have what is known as a transverse wave. Also, since the displacement is in the y direction, it is often referred to as a y-polarized wave. Since each point on the string moves on a straight line, the wave is also referred to as a linearly polarized wave. Further, the string always remains confined to the xy plane, and therefore it is also referred to as a plane polarized wave. In a similar manner, we can consider the vibration of the string in the xz plane generating a z-polarized wave whose displacement will be given by the equation 10.17. It should be mentioned that the linearly polarized waves, described by equations 10.15 and 10.17, are all transverse waves. That is, the displacement of each point of the string is always at right angles to the direction of propagation of the wave. Finally, if the plane of vibration of the string is changed randomly in very short intervals of time, then we have what is known as an unpolarized wave. Thus, for an unpolarized wave, the displacement will be randomly changing with time, though it will always be perpendicular to the direction of propagation. Light waves are transverse in nature. That is, the electric field associated with a propagating light wave is always at right angles to the direction of propagation of the wave. This can be easily demonstrated using a simple Polaroid. You must have seen thin plastic-like sheets, which are called Polaroids. A Polaroid consists of long chain molecules aligned in a particular direction. The electric vectors associated with the propagating light wave, along the direction of the aligned molecules, get absorbed. Thus, if an unpolarized light wave is incident on such a Polaroid, then the light wave will get linearly polarized with the electric vector oscillating along a direction perpendicular to the aligned molecules. This direction is known as the pass axis of the Polaroid. Thus, if the light from an ordinary source, like a sodium lamp, passes through a Polaroid sheet P1, it is observed that its intensity is reduced by half. Rotating P1 has no effect on the transmitted beam, and transmitted intensity remains constant. Now, let an identical piece of Polaroid P2 be placed before P1. As expected, the light from the lamp is reduced in intensity on passing through P2 alone. But now rotating P1 has a dramatic effect on the light coming from P2. In one position, the intensity transmitted by P2 followed by P1 is nearly zero. When turned by 90 degrees from this position, P1 transmits nearly the full intensity emerging from P2, figure 10.18. The experiment at figure 10.18 can be easily understood by assuming that light passing through the Polaroid P2 gets polarized along the pass axis of P. If the pass axis of P makes an angle theta with the pass axis of P1, then when the polarized beam passes through the Polaroid P2, the component E cos theta, along the pass axis of P, will pass through P. Thus, as we rotate the Polaroid P1, or P2, the intensity will vary as I equals I naught cos square theta, where I naught is the intensity of the polarized light after passing through P1. This is known as Malus law. The above discussion shows that the intensity coming out of a single Polaroid is half of the incident intensity. By putting a second Polaroid, the intensity can be further controlled from 50% to 0 of the incident intensity by adjusting the angle between the pass axes of two Polaroids. Polaroids can be used to control the intensity in sunglasses, window panes, etc. Polaroids are also used in photographic cameras and 3D movie cameras.
Hello, I'm Thomas Young. You might know me as a physician, but today I want to share a little story about light, one that changed everything. Let's step back to the early 1800s, a time when people fiercely debated what light actually was. Some said it was made of tiny particles, others believed it was a wave-like sound, others said a wave like water. Now, I was curious. What if I could settle this debate with a simple experiment? That's where my famous double-slit experiment comes in. Let me walk you through it. Imagine a beam of sunlight streaming through your window. I passed that sunlight through a tiny hole to make a narrow beam. Then I placed a card with two very close slits in its path. What happened next was quite strange. Instead of seeing just two bright spots on the wall, I saw a pattern of light and dark bands, an interference pattern. It looked like ripples in a pond when two stones are thrown and the waves overlap. Where the waves met in sync, you get a bright band. Where they cancelled each other out, there's darkness. Why is this so important? If light were particles, tiny bullets, you'd only get two spots, one per slit. But the pattern could only be explained if light acted like a wave. This was a huge deal. It suggested light behaved like a wave, not just particles. Of course, not everyone agreed at first. Some said my experiment was flawed, or I was mistaken. But over time, more scientists repeated it and saw the same results. The double-slit experiment became a cornerstone of physics, opening a new way of thinking about light. Years later, scientists tried it with single particles like electrons, and even those produced an interference pattern as if each particle interfered with itself. That discovery led to quantum mechanics. Things can be particles and waves at once. What started as curiosity about sunlight became one of science's most mind-bending discoveries. The double-slit experiment showed the universe is stranger and more wonderful than we imagined. Thanks for joining me on this journey.